Okay, last session we started with exponential functions. We started playing around with exponential functions, but what I thought we'd do today is backtrack just a little bit and then come back. Okay, so what I want to do is go back and make sure we have a good understanding of inverse functions, and then tie that into exponentials, and then show you as an introduction how your understanding of exponentials and inverses relates to something strange called a logarithm. So we'll start with a brief introduction. We'll try to get to a brief introduction on logarithms today. So what I did is based on a question I asked last session where I said, what's an inverse? And everybody looked like they had a glazed look about them. I thought it'd be worthwhile spending a couple minutes going back over that. So I picked some problems out of the book, and let's just start with a problem that involves finding an inverse. So if we took problem 58 on page 267, this is in your section 5.2, it says f of x is given to us as 4 over x plus 2. 4 over x plus 2. Now what I'd like you to do is write this down, and I'd like you to draw a quick sketch of this, and here's the thinking that I hope you have in your head, is this thing is behaving like a 1 over x graph that you should be familiar with, and then this thing is, that 1 over x would be transformed to being 4 times 1 over x. That's your 4 over x. And then finally, you get this thing which does what to it? What's the x plus 2 do to it? Careful. You're in here messing with x. You're replacing that x with x plus 2. Melissa, shifts left 2, right? So we have a shift left of 2 after it has been vertically stretched by 4. So draw a quick sketch of that and carefully plot a couple of points including asymptotes. If you're watching the DVD, then what I'd like you to do is pause the DVD and go ahead and do that sketch, and then we'll see if we all end up in the same place here in a second. What we want to do after you have this sketch down is what we want to do is form the inverse of this function, and then see what do the algebra, and then after that see what the sketch of it looks like. So we'll make a connection there. Okay, time's up. It should be very quick. Here's what I'm hoping you're able to do. And if you're not, you just need to practice a little bit more. 1 over x, you should know what that looks like. That's in our library of functions. It's a function that comes down and goes through 1, 1, and goes through minus 1, minus 1, those important points. So that's what 1 over x looks like, and that should be in your head, and it has a vertical asymptote and a horizontal asymptote. If you multiply 1 over x by 4, it's going to make it 4 times as what? What's it going to do to it if you multiply it by 4? Does it slide it up 4, or does it distort it? Multiply something by 4. Multiply your height by 4. What does that do to it? It distorts it. It distorts your height, doesn't it? So you're multiplying 1 over x times 4, so it's going to be 4 times as tall. So if you make it 4 times as tall, then instead of going through 1, 1, the point 1, 1, it's going to go through 1, 4. And similarly, at negative 1, it's going to go through negative 4. And so the graph of of 4 over x is going to be a graph that is 4 times as tall everywhere. 4 times as tall everywhere. And you should see a multiple of 4 on all these y values. All these y values should be, you should see a multiple of 4 occurring. So that's a graph of y equals 4 over x. Now, if you carefully then shift this 2 to the left by seeing the transforms in the equation we had back on the previous board here, shift it 2 to the left, you're going to end up taking the asymptotes with it. Look at this for a second. X equals 0 was the original vertical asymptote, right? If you replace that x with x plus 2, replace this x with x plus 2, then you can see that x equals minus 2 becomes your new vertical asymptote over 2 to the left. All right? And your horizontal asymptote, y equals 0, on the old original one, if you replace that with 4, right? 4 times as tall, okay? So if you replace that with y over 4 effectively equals 0, y still equals 0. So there's your horizontal asymptote remains the same. So the final sketch of this, after you've done the shift of this function f of x, and I want to draw it carefully, of 4 over x plus 2, is going to be a graph that's going to be shifted 2 to the left with x equals minus 2 as our vertical asymptote, and it's going to have a distortion by a multiple of 4 vertically on it. So 1 to the right of that vertical asymptote would be at -1. It's going to be up at a value of 4. So minus 1, 4 would be a point. Okay, and then if you put x equals 0 in, if you put x equals 0 into the function up here, f of 0 is going to be 4 over 2, which is a height of 2. So the y-intercept of this function will be at 0, 2. And that graph is going to be coming down off of near the asymptote, heading towards the horizontal asymptote there. And then similarly, off to the left, it'll be doing behavior like this. And if you're at minus 2, if you come over to the left, minus 1, minus 2, minus 3, what's the height going to be down at minus 3, at x equals minus 3, folks? At minus 3. You could go up into the function and put -3 in, but if you think of it in terms of the distortions, if you're 1 off the vertical asymptote, you should be up 4, and on the left side of it, down 4. This point should be -3, -4. Let's check those points out. F of 0 is 2. F of -1, -1 in here, add 2 to that, and you get 1, so you get a value of 4. That fits this point. And then finally, if you go over to the left at -3, further to the left, -3 in here, 4 over -1 is -4. So if you understand the distortions that you see, the distortion by a multiple of 4 and the shift to the left of 2, then you can nail these points down as we just did, but you can confirm it always with a function by going ahead and dropping in the input values and actually finding the output values. Okay, so that's a quick review of this relatively simple rational function. Here's the picture of it. Now, that's not what I wanted to address today. What I wanted to address today is the concept of forming the inverse function. How do we form an inverse? How do you form an inverse? Jennifer, yes. You interchange x and y. We're trying to make the machine go the other direction. The function go the opposite direction. So what we'll do is interchange the x and the y. And we have to do some algebra to do that. So let's do a little algebra now. So we have our function, which was y equals 4 over x plus 2. We're going to interchange x and y, and so we're going to get that x equals 4 over y plus 2. X equals 4 over y plus 2. And then, what do we need to do? Solve for y, always. Solve for y. Okay, well, this is a what kind of an equation? It's got a fraction in it. That's a hint.
Radical. No.
There's no radical here.
Fraction.
It's a fractional equation. It's got a fraction in it. It's a fractional equation. So what's your first step typically that you do to clean up fractional equations? Tyler? Multiply both sides by the common denominator, which is y plus 2, right? So multiplying both sides of this thing by y plus 2, we get y plus 2 times the x equals 4. And dividing by y plus 2, multiplying by y plus 2, you're going to lose the y plus 2's. Okay, so we get this. And don't forget, we don't want to lose sight of what we're trying to do here. What are we supposed to do here? Solve for y. So how do we solve for y? Probably distribute the x. And now here's the y right here now. So we need to isolate the y. So we're now going to kick all this stuff over to the other side. So we have y times x equals 4 minus 2x. And then we're going to divide both sides by x. And we're going to get 4 minus 2x over x. Okay, so we're reviewing the idea of forming an inverse. Starting with a function, which we know passes a vertical line test. And then we interchanged x and y. We identify this as a fractional equation. The technique for cleaning up fractional equations is always multiply both sides by the common denominator to get rid of the fractions. One step. Here it is. We now need to solve for y. So what we do then is distributed the x and move things around and solve for the y value. Any questions? Okay. So notice that this is a certain form. This would be called a general form of a rational function, wouldn't it? Linear function over linear function. Rational function, see it? And in its factored form, what would it look like? Help me. I know it's Monday.
2 on the outside of parentheses.
Pull a 2 out of the numerator. And so a factored form of this would be 2 parentheses 2 minus x over the common x. Okay? So there's your factored form. Here's the general form. And what if we took this and since it's a common denominator, and went ahead and imagined dividing this x up into the numerator? Look how easy it is to see right here. Isn't this a negative 2 right there? Negative 2. And then plus a 4 over x. So let me write it that way. Negative 2, the quotient, plus 4 over x. So there's the quotient form of this function. Can we draw a sketch of this? We should be able to. It's a rational function, linear over linear. And we have the different forms, so you can see the zeros and the vertical asymptote here. So if I draw it, We have a 0 at where? Where would a 0 occur? At x equals 2, we get a 0. Feel good? Vertical asymptote, folks? Where?
0, 0.
At x equals 0, dividing by 0 causes trouble, right? X equals 0. Vertical asymptote right there. And we label it. Okay, and then what else can you see? Though we just played with the factored form, and look at the quotient form. What can we see from that quotient form? Taylor?
An oblique asymptote.
Not oblique, but you're close. Y equals negative 2.
Or vertical. Or horizontal.
Thank you, horizontal. Y equals negative 2 plus, as large X happens, this heads towards 0. Let me write that down. If you're going way off to the right, then the Y value is approaching negative 2 plus this number, then 4 over a big number is close to 0, but slightly positive. So that indicates a horizontal asymptote, Y equals negative 2. Horizontal asymptote. A lot of people get mixed up by that, horizontal versus vertical. Think of horizontal as horizon. What do you see when you look out at the horizon? Nice sunset over the ocean. A horizontal line. Okay. So we have a horizontal asymptote, we have a vertical asymptote, we have a 0. So the picture, help me. You folks should be good at this. Picture. We know near vertical asymptotes they have to blow up or down, don't they? Okay, now we could do some testing like we've done previously. We could jump in. I didn't intend to have to reteach this today, but we could go in between a vertical asymptote and a 0, like some number between 0 and 2, like say, think of 1. Imagine putting a 1 in for x. Probably the factored form would be an easy spot. If you put a 1 in here, notice this numerator is positive and the denominator is positive if you're in this region between the vertical asymptote and here. So we're dealing with a positive divided by a positive, which has to stay positive. So blows up near this asymptote has to come through the 0. Now if you go out past the 0, out past 2, imagine putting a big positive number in for x. Big positive in here for x, what would you get? On the numerator, what's the numerator become of the big positive x? Negative, doesn't it? A huge negative value in there, divided by a positive. Negative divided by positive out in that region to the right of 2 has to be negative. And you can see that the horizontal asymptote is the limit that this thing approaches as you move out towards the right, and so it ends up dying, heading down towards there. If that looks like that, then what must occur over to the left? What would you expect to occur to the left? Where would you expect the picture to be? There's no zeros here. Down below here, good. And that's exactly right. The graph is going to look like this. Over to the left. Could you plot a point without having to do any algebra by even looking at the function, just looking at this picture we have? Could you help me?
Put a negative number for x.
Yeah, I don't want to look at the equation. All I want to look at is this picture.
So it's just the opposite. It's going to happen on the other side.
Where's this point going to be over here? It's going to be 2 to the left of the vertical asymptote, isn't it? Right? And then how far down is it going to be? What's this value going to be down here, folks? Look, if you're over to the right, and you're up 2 off the horizontal asymptote, then it makes sense that if you go symmetrically over here, you're going to be 2 below this asymptote, down at -4. Let's check it out by looking at the algebra. If you put -2 into the function, that becomes negative times a negative becomes +4. Plus 4 is 8 over -2. 8 over -2 is -4. Okay, that is the picture of the inverse, isn't it? That's the picture of the inverse. Don't lose sight of what we've been doing. We started with some other function, we interchanged the x and the y, and we solved for the new y, and here's the picture of that thing. So this thing originally was called f of x. The original function was called f of x, and this thing is a function, isn't it? So we can use what symbolism? That's not f of x.
G of X?
No. F with a little negative exponent or superscript here. Okay? So this is f inverse of x, which happens to be this thing right here, which is 4 minus 2x over x. So this is an inverse function. That's the inverse function. Melissa?
Why does it look the same almost as that one?
That's the nature of a kind of a reciprocal function that's been transformed. A reciprocal function that's been transformed will have the similar character to the other one. But all the x and y's have been interchanged. All the x and y's have been interchanged. I like the camera image right now because it's got this picture right back here behind me on the screen. So keep the camera image where you are for a second.